Hello, dear ORCA users. My name is Petra Pikulova and I'm a PhD student in the Department of Molecular Theory and Spectroscopy. And today it's my great pleasure to introduce a few new features that will appear in ORCA 6.1. I will mainly talk about the analytical calculation of Raman intensities, but I'll also briefly mention a few other things that are new in theoretical spectroscopy. So, to calculate Raman spectra, we need a few molecular response properties that describe what happens to the molecular system as we apply some external perturbations, namely distortion of geometry away from equilibrium and some external electric field. I have prepared an example. Here I have the hydrogen molecule, and I study what happens to the SCF energy if I distort away from the equilibrium distance. We see some kind of behavior that's often approximated with a parabola. And also what happens if we apply an electric field along the bond. So we see that there's also some kind of interesting behavior. And the thing we could do with a surface like this, if we wanted to describe it, obviously it's very complicated, and I have restricted myself to just these two dimensions. So what we could do is, if we look at this point without any perturbation applied, so equilibrium geometry, no field, we could expand the energy around this point as a Taylor series in some powers of the perturbation strength and coefficients that are always the derivative of the energy with respect to that perturbation evaluated at zero perturbation strength. And to calculate Raman spectra, we need particularly two terms in this series. So we need the Hessian, which is the second derivative of the energy with respect to geometric displacement. And from that we get the positions of the vibrational frequencies, and we also need the gradient of the polarizability tensor, which is already a third derivative of the energy, twice with respect to electric field and once with respect to geometry. And the polarizability gradient will give us the intensities that correspond to any given vibrational mode. Now, if we take a look at this surface that I have here, it's already kind of suggestive of one way that we could calculate the terms in this Taylor series, which would be finite differences. So we could actually take steps on this surface and collect the energies that we calculate, and then either use a finite difference formula or fit some function to extract the derivative. But that is not very computationally efficient, and it's also can suffer from some numerical problems. So it's much better to actually derive an analytical expression for the derivative and implement it for any given method. If we take a look at the capabilities of ORCA for DFT methods before ORCA 6.1, we have had the analytical Hessian implemented since quite a long time. However, the polarizability gradient has only been available as a numerical derivative. So in order to speed up the calculation of Raman spectra, make it more efficient, we have decided to change that and actually implement the polarizability gradient as an analytical derivative property. I would now like to guide you through the choices that we've made in order to make the calculation of that analytical derivative computationally efficient, because we're already dealing with a third derivative of the energy. And because we're basically doing perturbation theory, we can apply all of the tricks that we know from there. What I'm talking about is the 2n+1 rule, meaning in order to calculate the third derivative of the energy, of course we need the SCF solution, so the unperturbed wave function, but in this case we will also need the geometry. If we apply the 2n+1 rule, we will also need the geometric responses, and we will also need the responses of the wave function to the electric field perturbation. So we additionally need to solve 3 geometric response equations, where n is the number of atoms, and 3 electric field response equations. And that, together with whatever property integrals arise in the expressions for these properties, will give us enough information to assemble both the Hessian and the polarizability gradient. And from them, we can calculate the Raman spectrum. And the nice thing about this is that it's a one-step procedure where in one calculation you get both Hessian and polarizability gradient. Why I'm mentioning that is because there is also another reasonable alternative where we would choose not to apply the 2n+1 rule, but instead we would choose to solve for wave function responses still for the electric field perturbations, and then also the second order responses for the electric field perturbations. And there the nice thing would be that we would not have to solve for the geometric responses whose number grows with the system size, and we could still get the polarizability gradient. However, there arises a question, because in this scenario we would not get the Hessian at the same time, because the Hessian always needs the geometric responses. So we would have to either get that from some other calculation or solve for the geometric responses anyway, which kind of diminishes the attractiveness of this alternative scheme. So previous authors who have worked on analytical Raman intensities have chosen either one or the other. We have given preference to applying the 2n+1 rule. So within that 2n+1 rule approach, we have derived expressions and implemented analytical Raman intensities for Hartree-Fock theory and DFT functionals up to meta-GGAs, including things like hybrids, range-separated hybrids. And we have also extended the program in a few ways, so it's consistent with effective core potentials. It works in case you use some scalar relativistic Hamiltonian. It also works in case you have some external point charges, and it has also been implemented for implicit solvation with CPCM. The main limitation is that we have restricted ourselves to only static perturbations, so for dynamic polarizability derivatives you still need to use the numerical approach so far. So in order for the program to be efficient, the first important things we've already done: do it analytically, choose the 2n+1 scheme. After all of that is done and settled, it's time to ask if we could approximate some expensive terms with well-known approaches to reduce scaling. So the most time-consuming part of assembling the polarizability gradient once the responses of the wave function are there is calculating this contraction of two electron integral derivatives with densities perturbed by the electric field. And it's possible to apply Rij and cosx to terms like this. So as a brief reminder, Rij is usually used to speed up constructions of Coulomb or Coulomb-like matrices, and the basic idea is to expand products of basis functions in an auxiliary basis set so that the Coulomb matrix or energy is then constructed from 3-index and 2-index quantities rather than from the 4-index two electron integrals, while cosx is a semi-numerical approach where one of the integrations needed to construct the integral is done analytically, while the other one is done numerically on some finite real space grid, and this allows you to screen contributions effectively. And we have implemented both of these for the calculation of Raman intensities, speeding up both calculations with pure DFT functionals and hybrids. So we can take a look. I've got here some scaling with the length of a linear alkane chain with the number of carbons. So we can see that if in case the two electron derivative is done exactly, the calculation of this term will eventually dominate the computational time for constructing the property. while if we apply cosx and Rij, these two contributions are somewhere here in the dust, and the computational time is reduced. So now that we've applied some approximations, it's relevant to ask whether we still have the desired accuracy. We have examined that a little bit in a set of 18 small molecules. So running a calculation with Rij, we have found that if you use a sufficient auxiliary basis set, then the errors that you get in the matrix elements of the polarizability derivative lead to such errors in the Raman spectra that if you plot the spectrum, you will probably not notice at all that there's some difference, which is very good. And then looking at the hybrid functional, if we take a look at what happens with using cosx on top of, in addition to just Rij, the error basically does not get worse with the default grids. So these two approximations should be safe to use and speed up the calculations quite a bit. And now it's time to look at how the method is performing compared with what was there previously. So the numerical approach, obviously any speed up that you get is some kind of function of system size, grid size, basis set size, and everything. So I've just taken some slice through this many dimensional space and again done this scan with the length of the alkane chain. And what I've observed is that with exact integrals, basically, first of all, basically in all cases that I've seen, you always get the analytical derivative is always faster. And with exact integrals, I have seen speedups up to maybe 7 times. With the Rij cosx implementation, I have also frequently seen speedups of maybe 15, 16 times, which is really worth having. The program is parallelized, and it is decently parallelized. So here I've investigated what sort of speedup you observe if you go to up to 32 cores. So in assembling the polarizability derivative, the speedup is excellent. That's like 29 times. The speedup for the total runtime is also very decent. And now that I've hopefully demonstrated that the program is efficient, I'd like to show you the biggest thing that I've thrown at it, or that I've thrown the program at, which are the Raman spectra of these cucurbiturials. So cucurbiturials are macrocycles that are often used in supramolecular chemistry. They are oligomers of glycoluryl, and a while back there was an experimental study where they measured Raman spectra of cucurbituryl 5 to 8 and observed some systematic shifts in vibration frequencies. And so I calculated that using the Rij cosx approximations and going for a relatively big basis set, def2 QZVPP. And first of all, a nice thing is that I've seen the same systematic trends, maybe more for demonstrating the program capabilities. So the largest cucurbituryl has 144 atoms, and with def2 QZVPP that was near 7,000 basis functions. And I think it's a good success that this is already a big calculation, and doing the polarizability derivative and the Raman spectrum on top of just doing the Hessian introduced only about 7% overhead. So now it's time for you to go and pick your big molecule to throw into this program. And if you want to do that, I have picked here a nice example input. So this is actually from the ORCA tutorials on the FACTS website, the infrared and Raman, this benzene example. The input is very simple and it follows what was there previously for the numerical derivative. So if you ask for a Hessian or for the frequency calculation at the same time as the polarizability, The program will do the Raman spectrum automatically, and then in your output you will find enough data to assemble a table like this with frequencies, Raman activities. And I also wanted to point out a nice tip, because in ORCA 6.1, if you use symmetry and the program detects some symmetry, then the modes will be automatically labeled with the irreducible representation that they belong to, which is super convenient for vibrational spectroscopy, and it's one of the results of the good work that Axel Koslowski has been doing on introducing symmetry to ORCA. Which leads me quite naturally to what else is new in theoretical spectroscopy in ORCA 6.1. So one thing I wanted to mention is that it's now possible to also calculate another third derivative property for basically the same range of methods as the Raman intensities. This is the static hyperpolarizability. It's simple, you ask for it in the LProp input block. Another exciting feature is or a group of features is the result of work of my colleague Marcos, who implemented a few high-level methods to calculate core-level excited or ionized states for open shell systems using core valence separation. So you can find out more about that in his paper or in the ORCA manual. And last thing I wanted to mention is that my colleague Tiago has worked on connecting his method, general spinroses, with quasi-degenerate perturbation theory. So now you can calculate some magnetic properties, and this is useful for MCD, XMCD spectra. That was all from me. I would like to thank my supervisor, Professor Neze. I would like to thank the ORCA development team, who work very hard to make the lives of us developers easier. And I would like to thank all of you for your attention, and hope that now you go and do something very cool with ORCA 6.1.